Hi and welcome to this clip going through question 1 of the June 2018 Cambridge Chemistry Challenge paper. So let's start by looking at the front cover, the top sheet that comes with every Cambridge Chemistry Challenge paper. It has some useful information there to help settle you and sort of get you moving on the paper. So the first thing to have a look at is the fact that there's a box there that tells you that some of the material might be familiar to you, but some of it won't be, it'll be new. They're more difficult questions on a Cambridge Chemistry Challenge paper, and they're meant to make you deduce as opposed to just memorise or recall, which is a skill that sort of feeds over from GCSE. So in terms of your maths skills, it's always a good idea to make sure you're using the correct units and the appropriate number of significant figures. For example, the least sensitive as provided in the question. When you're writing your answers, try to keep them brief and concise. Don't find yourself waffling or writing tons and tons of sentences or text. They're more interested in bullet points because that shows that you stick to the point and you know what you're talking about. So as you'd probably expect in a normal A level, this is likewise here, but even more so because it's more challenging, so let's just stick to the key points you need to make. So when using the periodic table that's provided with the paper, don't try to use relative atomic mass values that you might have memorised or happen to know in the back of your head from your normal data sheet or periodic table that your exam board provides, because the C3L6 periodic table is often to 2 dPs or even more. If you look at some of the values, for example, they're at least 2 dPs, sometimes even further than that. So looking at the question, you can see from the opening paragraphs that it gives a context against which the chemistry that's being tested during the course of the question is actually set. So the purpose of this is to show you one of the real-life applications of the ideas that are covered. So let's get started. So looking at the first question, it's asking you to split anorthosite, which is the calcium aluminium silicate mineral that's commonly found on the Moon, into simpler compounds such as silicon dioxide and aluminium oxide. So if we remove the calcium temporarily from the formula, you can see you've got 1 mole of Al2O3 and 2 moles of SiO2. So you start by working out the molar mass of your anorthosite, which is 278.22 grams per mole. And you do the same for the two components, the two simpler oxides, aluminium oxide and silicon dioxide. So the percentage by mass is quite straightforward. You just take the molar mass of your simple oxide, divide it by 278.22, and then times by 100. So not forgetting, of course, that you multiply the molar mass of your simple oxide times the number of moles that is present. As you can see what we've done in the silicon dioxide example, you get 36.6% for aluminium oxide and 43.2% for silicon dioxide. On the next question, it talks about getting oxygen from ilmenite, which is an iron titanium oxide. So obviously if the Moon is going to be terraformed, which is what we're talking about here, you're going to need to have a source of oxygen. So they're thinking about how you can get oxygen from the minerals that are present there for us to breathe, or for astronauts to breathe. So one of the methods being suggested is reducing the ore with hydrogen brought over from Earth to produce iron, titanium oxide and water. And it says during the reaction the titanium remains in its maximum oxidation state throughout, and the water form may then be electrolyzed to reform the hydrogen and therefore liberate oxygen. So the first question is, by considering its position in the periodic table, what is the maximum oxidation state of titanium? So let's get the periodic table onto this page. So the first thing to do is to look at its oxidation number via the number of electrons it has. And in its outer shell, it's got 4 electrons. And because it's got 4 electrons available for bonding, in other words, the definition of oxidation state is the number of electrons an atom has or makes available for bonding, it must be +4 as its main oxidation state, or its maximum oxidation state. So there was obviously a reason they asked you about the oxidation state first before they asked you to give the formula of the two oxides that may be thought of as making up the mineral ilmenite. Because if we take titanium as being +4, that would mean its oxide would be TiO2. And if it's FeTiO3 as the formula for ilmenite, then the only thing you've got left after taking away TiO2 is FeO, or iron 2 oxide. So the next part asks you for the equation for the reaction between ilmenite and hydrogen. Now in the text it tells you that it produces iron, titanium oxide and water, which is easy enough, and it says the titanium remains in its maximum oxidation state throughout. So that must mean that the titanium oxide that's produced is actually TiO2, the one that we've just thought about. So the next part asks you to calculate how many tons of moon rock would be needed using ilmenite to produce a ton of oxygen gas using this process. So first of all we need to start working in grams. So 1 ton is 1 million grams. So by dividing the number of grams in 1 ton by the relative molecular mass of oxygen molecules, of oxygen gas, you can work out how many moles you'd get in 1 ton. Now in the question it says that the way they get oxygen from the ilmenite is by electrolysis of the water that's produced in the equation in part 3. So that means that you get half a mole of oxygen from every 1 mole of water. So because it's in the question it says the average titanium content of the rock used in the process is 2.5% by mass, we have to work backwards from titanium mass. So looking at the equation in part 3, the grams of titanium can be worked out from the moles of titanium. So the mole ratio of titanium to water is 1:1. So therefore the mole ratio of titanium to oxygen is 2:1. So therefore you get 62,500 moles of titanium being used to make 32,150 moles of oxygen. And that amount of titanium equates to 2993750 grams. So now what we've got to do is to work out what is that 2.5% of. So working that up gives us 120 tons when it's converted to 3 sig figs. So the next section asks you for an equation which involves the reduction of the iron species present in ilmenite using methane. And it says in the first step 1 mole of methane reacts with 1 mole of ilmenite to form 5 moles of products, so 3 moles of which are gaseous under normal conditions. So let's just put down what they've given us first. So they tell us that there's 5 moles in total of products and 3 moles of gas. So looking at the things that could be gaseous, you could have water, you could have carbon dioxide. Does it say what actually happens? It says reduction of the iron species. Now, reduction of the iron species would suggest that Fe is produced. Now, there was another reduction that we looked at earlier in part B, and in that equation it suggested that TiO2 is made. Now, this is also a reduction, so let's go with TiO2 being one of the products as well. So now we've got 2 products, 2 moles rather, and we need to come up with 3 moles of gas. So you'd be able to get 2 moles of hydrogen gas for every mole of methane. That leaves carbon. You've used up 2 of the oxygens from FeTiO3. There's only 1 oxygen left. So because you only have 1 carbon and 1 oxygen left to play with, that must mean that the other gaseous product would be carbon monoxide, not carbon dioxide. So moving on to the next question, it starts to get a bit harder now. This is talking about oxygen from silicates, but it's coming at it from a different angle. It's talking, instead of percentage by mass and equations and moles, we're looking at thermodynamics now. and that includes something called entropy, which is, if you're doing the Cambridge Chemistry Challenge, you might not have come across before, because the Cambridge Chemistry Challenge is a first year paper and entropy is normally a second year topic. But it should give you enough information throughout the question to help you on your way. So throughout this bit, it's important to look out for things that might help you, because they'll give you information that will help you problem solve or deduce your way through this part. So let's go down to part D. So this part is about the reaction in the equation that's given, and it says, on heating with the gaseous products of this reaction, although not necessarily in the ratios formed, with a nickel catalyst the methane is regenerated and water is also formed, which can later be electrolyzed. Obviously earlier we looked at how that electrolysis could produce oxygen to support humans living on the moon or working on the moon. So it asks for the equation for this reaction to regenerate the methane. So working along the lines of the simplest molar ratio to produce 1 mole of methane, you would need, if you were producing water as well, enough hydrogen to produce 6 atoms of hydrogen on the right hand side, split between methane and water, so therefore 3 H2s is required. And obviously carbon monoxide would be the source of the carbon in the methane. So the next section, it says the standard entropy change, delta Rs, gives a measure of the change in the amount of disorder that takes place during the reaction. And it gives you a little equation, amount of disorder in the products minus the amount of disorder in the reactants. And it then asks you to say, would you expect delta Rs for the reaction from the equation we've just written to be positive or negative? So taking the idea that gas is more disordered than a solid, and in this case we only have gases, we can assume that the greater the number of moles of gas, the greater the entropy, the greater the level of disorder. So if you look at the reactant side, you've got 4 moles of gas, but on the product side you've got 2 moles of gas. So if you take the amount of disorder in the reactants away from the amount of disorder in the product, without actually putting the entropy values in, we can predict that the entropy value will be negative. So the next question asks you to calculate the standard enthalpy change at 298 K for the reaction between magnesium silicate and methane. And because the data that we have is enthalpy of formation data, that means we've got to draw our Hesse cycle using the constituent elements in the correct mole ratios, which I've done in that little box there. So we can construct a Hesse cycle and put in the values from the data table. So following it around from start to finish, that gives us 876.7 kilojoules per mole. So the next thing we have to do is the standard entropy change for the reaction between magnesium silicate and methane. So to calculate delta Rs, you have to look at the total entropy of the products minus the total entropy of the reactants. So putting those numbers in, noting that they're quoted in joules per Kelvin per mole, that gives you 518.8 joules per mole per Kelvin. You can write it joules per Kelvin per mole, either way around, it doesn't really matter. Okay, so now we can go on to part E. And it introduces a new thermodynamic quantity called the standard Gibbs energy of the reaction, or delta G. Now this equation is something that you might not have come across if you're first year, but you'll definitely come across it in your second year, like I said earlier. So it gives you a bit of information, and if delta G is positive, it means the reactants are favoured at equilibrium, and if delta G is negative, it means the product is favoured at equilibrium. So putting this into context, if delta Rg is negative, then that means the reaction is spontaneous. It'll go by itself because there's free energy available to do that work that's needed to push that reaction in the forward direction. And if this value is positive, what happens this time is the reaction, the forward reaction that is not spontaneous, so it's unlikely to go by itself. there's no free energy available to do the work needed for this to happen, so the reverse reaction is favoured. So just something to point out in the calculation, although delta H stays the same as we calculated earlier, I've had to change the entropy value, 518.8 joules per Kelvin per mole, into 0.5188 kilojoules per mole, remembering that 298 is in Kelvin, so therefore you multiply by Kelvin and then divide by 1000. So that gives you kilojoules per mole to the minus 1. So that gives us 721.5 kilojoules per mole. So we need to now work out whether the reactants or products are favoured at this temperature. So the conditions described on the screen at the moment, the reverse reaction being favoured, are the case at the moment because it's a positive value for delta Rg, so therefore reactants favoured. So the next section says that assuming that the values of delta Rh and delta Rs don't vary with temperature, calculate the minimum temperature at which the products will be favoured. So here what we've got to do is assume that delta G equals 0. So that means that T must be equal to delta H over delta S, which gives us 1690 Kelvin. Obviously that's 4 significant figures still. So by the time you get to the end of the question, it's usually the hardest part. So the idea behind the rationale of the paper is that by this stage you've got some momentum going, you probably picked up a few marks, and you're more thinking, you know, I've got this far, let's try this, rather than, ouch, that looks really difficult. Now there's a rather horrible looking equation there, but we'll see what we can do with it as we work through it. So this section is about ion-plasma separation. So it's again about looking at getting oxygen, but this is a method that requires very high temperatures. So the moon rock is heated by concentration of the sun's rays, using energy that's already available on the surface of the moon. So at 8,000 degrees C, every single bond in the sample is broken. So therefore we have something called atomization. If you're in your second year, you'll come across this as well. If you're in your first year, you might not have heard of the idea of atomization, but just take it as meaning all the bonds in the sample are broken, so just atoms are floating around. Now some of these atoms have electrons knocked off them, just like would happen in a mass spectrometer, so therefore you get positively charged ions. And the positively charged ions and the other particles that might be formed can be separated using magnetic fields, because that's exactly the same idea that the internal workings of a mass spectrometer is based on. So they give you a sort of fictional rock, might be a real one, but they just say suppose a rock is composed of the elements oxygen, sodium, magnesium, aluminium, and silicon, arranged in order of increasing atomic number. It asks you to arrange these elements in order of their first ionization energies, starting with the easiest to ionize. So in this case, you need to think of the factors that influence nuclear attraction, which is basically what you have to overcome during first ionization energy. So thinking back to the ideas you would have come across early on in your course, in your first year, things like shielding, shell number, or number of shells rather, atomic radius, and also the number of protons in the nucleus, so therefore the nuclear charge. So thinking about the elements in terms of their placement in the periodic table. So sodium is the easiest to ionize, then followed by aluminium, then followed by magnesium. So remember that aluminium has an electron filling a new subshell, so it's going to take a dip a little bit from magnesium. It's an important one to remember, so it's not simply going across the period. And remembering that oxygen is the most electronegative one of all of them, so it's going to be the highest. Okay, so let's now go down to part G. So what they want you to do in part G in the first part of it is deduce what units the constant C must have. So if we have a look at the expression, you can see what cancels out. Because by doing so, you can save yourself some work. So looking at all the individual units, you can see that kilojoules per mole to the -1 cancel each other out. And so does joules per Kelvin to the -1 per mole to the -1, and also Kelvin. So therefore, CE to the -EI over RT cancels completely. So that leaves us with T to the -5 over 2. The units being Kelvin to the -5 over 2.